In this video, we will be talking about the electric field, as we already have, but now we're going to look at it for a distributed charge. What happens when, there's not just a point charge or a shell of charge? So before we get into that, we have to talk about two different types of material when it comes to charged objects. There are those that are considered insulators, and insulators are objects where charges cannot flow or move around on them. Wherever you place the charge, it stays there. And it can be placed in any arrangements. You could have a particular density of charges, you could have it all in one spot, etc. On the other hand, conductors, charge is free to flow and it will arrange itself in a very predictable way. The most predictable is a sphere or shell of metal, of conductor, and the charges will spread out evenly on that exterior surface. So if we want to figure out the electric field for charge distributed in various different ways, there are three different situations we can look at. And you can probably follow along with this video on page 16 in your packet. That will give you some of these examples and you can jot down some notes. But if it's a point charge, we use Coulomb's law. And if we have, 3 or 4 point charges, we can add them up as vectors. Then there's the way we do it with distributed charges, what we're going to looking at today, the second method. And we basically take Coulomb's law, but we integrate it. We add up the effect of bits of charge in some predictable arrangement along a shape, some volume. We're going to have to switch from charge dq to volume or spatial coordinates, things we've done before as well with doing moment of inertia and center of mass. And line segments, arcs, rings, disks, etc. We can use for this. And then we will get to a little bit later, highly symmetric arrangements, a sphere, a shell, a line, a cylinder, or a plane that is infinite. And all of those come up with some really interesting results. So we'll get there. The first example was this from yesterday, whenever the last video was, when we did Coulomb's law. Shell theorems apply, you add them up as vectors. The second method also works for these same kinds of situations, but we'll get to that in a moment. So if you think of a solid conducting sphere, as I said, if it's a conductor and you put some negative charge on it, in this case, -2 times 10 to the -5th coulombs, then it will spread out evenly on the outer surface. There will be no charge distributed through the middle. It'll just be on the surface. So inside of this shell, right, we could think of it as, even though it's a solid sphere, inside of it, we could think of it as a shell of charge. So if we think about the electric field at 30 centimeters from the center of this, where point A is, which is still inside the shell, it's going to be 0 because of the shell theorem. Because if you were to place a positive test charge there, it would experience no net force from all of that charge in a shell. What about at the surface? So right on the surface at point B, notice it's slightly outside, right? We're on the outside edge, but we are basically at a radius of 1.2 meters from the center of the shell. Well, for this, we're going to use Coulomb's law for point charges. 9 times 10 to the 9th for our electrostatic constant, Newton meter squared per Coulomb squared, multiplied by the charge in coulombs. Notice I've dropped the sign because I'm really just interested in the magnitude here. We'll determine the direction in a moment, and divided by the distance from the center of that spherical arrangement. We get 1.3 times 10 to the 5th newtons per coulomb, and it is going to be to the right or inward toward the center of the sphere, right? Because that's how a negative charge would apply a force to a positive charge. We don't want to plug in the signs of the charges, mostly because then we have to figure out what that sign means. It's much simpler to just think about this conceptually, find the magnitude, and then realize that electric field lines always point toward negative charge and away from positive. So we could make a graph and think about if you were going radially out from the center of this sphere, if capital R is the radius of the sphere, then you would say that from 0 to R, the electric field is 0, that blue line. And then from R out to infinity, it goes like 1 over R squared. Something like that. It's not exactly a 1 over R squared line, but you get the idea. So 0 electric field, then it jumps up to maximum at R when you're on the surface, and then it falls off as you go outward. Right? It's proportional to 1 over R squared out there. So let's look at the second method. And we're going to use this basic idea that the total electric field is the sum of the little bits of electric field. Now, this should not be surprising. We've done this before, and this is essentially using the rule of superposition, that we talked about last time. But instead of discrete individual particles, maybe 2 or 3 of them, we're talking about an arbitrarily large number of little bits of electric charge, creating little bits of electric field. And so that little bit of electric field comes from K, our constant, times a little bit of charge, dq, divided by r squared. So what are our steps? First, we have to convert this vector integral to a scalar integral. And so that is important because we really are looking for the magnitude of the electric field. But this is adding up vector sums, and so that's non-trivial. It's not something we can just do. We'll talk about how we might do that for various arrangements. If it's a line, a surface, or volume integral, we need to make the appropriate substitutions for the little bit of charge, right? If you have charge along a wire, right, that's a line integral. Instead of dq, we would use, d lambda dx, or something like that. If it was a volume, it would go to dv. And then we want to express the integral in terms of a single variable, right? X, Y, or Z, or R, or something, or theta, or something like that. Then figure out what the limits of the integral are and actually do our integration. So that's what we're going to practice. So if you have a charged line, ring, or arc, basically something that could be described as a linear arrangement of charge, the linear charge density, lambda, so many coulombs per meter. Then we would say, well, our bit of charge is lambda, that charge density, times a little bit of length, dl. We use dl instead of dx here because it could be in an arc, it could be in a circle. So we'll replace that with x or r or r theta or whatever we need as we get there. For a charged surface, so that would be like the surface area of a cylinder or a sphere or even just a plane, something like that, we would use sigma, surface charge density, coulombs per meter squared. And we would replace the little bit of charge with that surface charge density times a little bit of area. Sometimes you see it as d lowercase a, sometimes you see it as d capital A. And you'll see that. Then there is rho, the volume charge density, coulombs per meter cubed. And for that, you replace it with a little bit of volume. And again, sometimes you'll see them use a lowercase v, although probably a capital V for dV would make more sense given what we usually use for volume. So how do we do this? Well, for a linear arrangement of charge, here I've got a rod, that has some positive charge on it. We say that it's 36 centimeters long, and we're interested in the electric field out at point P, 8.5 centimeters away from one end. So we know the charge density, 6 microcoulombs per meter. We have the length of everything. We've got all the dimensions. So what do we do first? Well, first we have to say, well, the little bit of electric field is k dq over r squared. I can't add up, some from the first dq to the last, so I need to switch this into linear or spatial coordinates, right? And so what I do is I think of a little bit of dq, that's the little orange block there. And if I move across there from one end to the another, I can add up the effect of all those little bits of dq. And that little dq provides a little bit of dE, or the smallest amount of electric field that we can have. And since these are all positive charge, it would all be away from the charge. So each little dE points to the right. That means we can drop the vector nature because we know every bit of this positive charge is going to create a vector to the right at point P, and we can simply add up their magnitudes to get the total magnitude of the electric field. Now we need to substitute that dq, because as we talked about before with mass and center of mass and moment of inertia, you can't really differentiate 1 kilogram of matter from another. Similarly, what's the difference between one elementary charge and another? They are fundamental. They don't look different. They're not numbered. So instead of this, we're going to integrate from some position to another position. So we're replacing r with x because we're moving along the x-axis. And instead of dq, it's lambda times dx. So now we have something we can actually integrate. In order to do that, we're going to integrate from our initial to our final position. Whatever that ends up being, we can take the actual integral and we end up with This, we're going to start at 44.5 centimeters because that's how far away we are from P when we're at one end, and then go to 8.5 centimeters because that's how far we are away at the other end. And we can come up with an answer here. We end up with 5.1 times 10 to the 5th newtons per coulomb. And again, to the right, because we already determined that that was the direction. So what we've done is we've broken up this rod or this line of charge into arbitrarily small little bits of charge and said each one provides some electric field to the right. We add up all these pieces, and then we get the total electric field at that point due to this line of charge. We can do this for other shapes, differently shaped arrangements of charge. In this case, an arc of charge. So it's just part of a circle. Point P is at the center of the circle, and we've picked this spot because it makes it possible to do the calculation a little more easily. The radius of the circle is given. This is a total amount of charge instead of being a charge density, so that's a little bit different. The good thing about this is that our distance from our point to our charge, or from our charge to our point, is the same always. Our little DQs are always the same distance away, and the electric field is going to be the sum of all of that. Unfortunately, we do have a problem. Well, I guess not unfortunately, but the little bit of electric field from this DQ is, kind of exactly opposite that off of the circle, but that one's that way. So we need to come up with a way to deal with this so we don't have to worry about a bunch of different vectors at different angles as we integrate across. And so the way we're going to do with this is make the argument that all the x components left and right are going to cancel by symmetry. And that's because for every dq on the right-hand side, there's a corresponding one on the left-hand side, and their x components will cancel. We just have to add up their y components, which is good. But the y component of this individual little bit of electric field is going to be dE times the cosine of theta because of the geometry of this problem. Right? The sine would be the x component in this case, and the y component would be the cosine. So I'm going to put myself over there. And theta is always measured from the midpoint, so that we've got sort of a negative and a positive theta, and they all have a corresponding extra piece. So that means that the total, and I will keep trying to move my video out of the way, I guess that's not too much in the way, the net electric field is going to be straight down because all the x components cancel. So how do we actually do this? Well, we now have this relationship that says the net electric field strength is going to be equal to the integral of k dq over r squared, our standard Coulomb's law piece for integrals, times the cosine of theta. But of course, we have to replace the dq. We've already done that. dq has to be replaced with a lambda times a distance measurement. But in this case, it's a little bit different. The r squared is just capital R squared because every bit is the same distance away. But as we go along the arc, we have our little ds. But we're not quite done with our substitution because we have s now as a variable, r is a constant, and also theta. And we need to combine do something else, one more substitution to get rid of that. We know that the arc length is just the angle multiplied by the radius of the circle, right? That's what we know from looking at circles. And so we can say theta is s over r, or ds is going to be r d theta. And so we're going to replace that ds with r d theta, as shown here. Then we're integrating a bunch of constants times cosine of theta d theta, which is something we know how to do, or at least can look up. And we're integrating from negative 45 degrees to 45 degrees. This is an arc of charge. That's what we're told. So it's basically a half circle, a quarter circle, from 45 to negative 45 to 45, so 90 degrees of a circle. And if we do that, we end up with root 2 k lambda over r. Now, the exact amount here isn't super important, except to see that what we have is Q, our total charge, because that is what we mean by, if you think of what lambda is the total charge divided by the quarter arc length, which is 1/4 of 2 pi r. And so we can actually plug that number in and we can finally get a value there. So that's it. that is the method for integrating lines and arcs of charge. We're going to stop there. Let us think about that for a little bit before we go into some additional methods or additional example problems where we go to surface and volume integrals, which adds a little more complexity.